Okay, AP Calculus AB, Unit 6, Day 3, office hours. So I gave you guys some tips before about how to start some of these problems. So your circle inscribed in a square, and figure shown the circumference of the circle is increasing. The circumference of the circle is increasing at a constant rate. So that'd be dc dt is positive 6 inches per second, increasing at a constant rate. As the circle expands, the square expands to maintain the condition of tangency. Note a circle with the radius r, circumference equals 2 pi r, and area equals pi r squared. Find the rate at which the perimeter of the square is increasing. Indicate units of measure. So we're looking for dp/dt. Now, we have dc/dt. The perimeter is the perimeter of this square, right? Indicate the perimeter square. The perimeter square is 4 sides. So we need to, we got to get, I don't know, we have circumference, which isn't really directly related to this, but we could get probably dr dt from the circumference. And then since each side of the square is 2 r's, then if we had dr dt, we could find dp dt. So I think we're going to start with trying to find dr dt. So dr dt, I would use this circumference right here. So we take the derivative of it implicitly with respect to time. dc dt equals 2 pi dr dt. And since dc dt is 6, and we don't even have to know the radius, so this is a constant rate of change also. So dr dt equals 3 over pi divided by 2 pi, right? 3 over pi. The units are inches per second. So that's dr dt. And we could now go back to our perimeter and do dp dt, derivative perimeter with respect to time, equals 8 dr dt. And we just found that dr dt is 3 over pi. So dp dt equals 24 over pi. The units are inches per second. So that seems good. So that was part A. Part B says at the instant when the area of the circle is 25 pi square inches, find the rate of increase in the area enclosed between the circle and the square. Indicate units of measure. So the area between the circle and the square. So I kind of drew that picture earlier. So the area between the circle and the square would be the area of the square minus the area of the circle, right? And that would be side squared minus pi r squared. And the sides, we already said we could treat as 2r each, so we get everything in terms of one variable. And so we get 4r squared minus pi r squared. So this is the area that we're trying to talk about. So if we take derivative of this, then we'll need dr dt, which again we already found for part A. So we're going to take the derivative implicitly. dA dt equals 8r dr dt minus 2 pi r dr dt. All right, power rule first, multiply by 2, decrease the power by 1, but then you got to follow up with the derivative of what's inside, implicit. And we need one more thing. We got to figure out what r is this time. And they said at the instant when the area of the circle is 25 pi. And so the area of the circle is pi r squared. So r equals plus or minus 5. That's what we need. So dA dt equals 8 times 5 dr dt plus 3 over pi minus 2 pi r is 5. dr dt is 3 over pi. Here the pi's cancel. And so we get 120 over pi minus 30. And the units should be area over time. So the units of area should be something squared. In this case, it's inches squared over time is seconds. And if you were to calculate this as decimal, it should come out positive. Like that area should be getting bigger. So there you go. Kind of a interesting version of that. Next one. We have the balloon, like a balloon animal balloon, and so then I give you the hint that like you think of it as a sphere and a cylinder together. So the sphere has a height, or the cylinder has a height. The sphere and the cylinder both have the same radius. So the total volume is the volume of the cylinder plus the volume of a sphere. The two half spheres make a full sphere. Pi r squared times 4/3 pi r cubed. So we're going to probably use that. At this instance, what is height? Okay. The balloon is shown above in the shape of a cylinder with hemispherical ends of the same radius as that of the cylinder. The balloon is being inflated at a rate of, so that's dV dt. dV dt equals 261 pi cubic centimeters per minute. At the instance that the radius of the cylinder is 3 centimeters, the volume of the balloon is 144 pi cubic centimeters, and the radius of the cylinder is increasing at a rate of 2 centimeters per minute. Increasing. Pause. Okay, at this instance, what is the height of the cylinder? So the part A is really just I feel like a geometry question. So this is kind of all the key information. So what is the height of the cylinder? So volume equals, well, we have the volume is 144 pi at this instance. Equals pi, the radius is 3 squared. H is the thing we're looking for, plus 4/3 pi, the radius is 3 cubed. So we just need to solve for H. A little bit of geometry, algebra. So we could divide a pi out of everything, right? So we have 144 equals 9H. Here, one of those threes goes away, so that's 36. So subtract 36. 14 minus 6 is 8. 0, 1. 9H divided by 9. H equals 12. Units are centimeters. Okay. Probably need that though. Yeah, a lot of times if they ask you to do that in part A, you probably need it for part B. At this instant, how fast is the height of the cylinder increasing? So we're looking for dH dt. Now we have this volume up here that has R, H, and V. So we have dV dt, right? And we have dr dt. So this one is okay to leave with 3 different variables. You just got to be careful when you got to, take the derivative. You have to do a little product rule. So dV dt equals, we could do pi r squared dH dt plus 2 plus h times 2 pi r dr dt. So that's all that product rule right there, the first term. Right? So you do pi r squared times root of that, and that times root of this, plus 4 pi r squared dr dt. So that's your implicit derivative with respect to time. And now we just, this is what we're looking for, right? But I think we have everything else. I don't even think, do we? Yeah, okay. So dv dt was positive 261 pi. And then r was 3. And then h was 12. We just found that. R was 3. dr dt was positive 2. R was 3. And dr dt was positive 2. So now we just got to solve for dHdt. There is a pi in every term, so we divide a pi out of everything right away if you want. So we have 261 equals 9 dHdt plus, this is going to be 12 times 12, 144, plus this is going to be 9, 36, 72. So 9 dHdt equals 261 minus 144 minus 72. I don't know if that's the best way to do that. What would this be together? 6, 11, 216. Let's just do it that way. 2, subtract 216. So 11 minus 6 is 5. 5 minus 1 is 4. 9 dH dt equals 45. Divide by 9. And we finally get a very nice answer. dHdt equals 5. What are the units? H should be one-dimensional units. Centimeters per first power over time is minutes on this problem. And it came out positive, which it should. Since everything's increasing, the height should be increasing too. All right, number 3, trough. The trough shown figures 5 feet long. Vertical cross sections, inverted isosceles triangles, inverted upside down isosceles triangles. Base of 2, height of 3. Water is being siphoned out the trough at a rate of 2 cubic feet per minute. So it's coming out or out the top or something. Siphon usually is out the top, like with a hose. So dv dt equals negative 2 cubic feet per minute. We're losing water out. Anytime t, let h be the depth and v be the volume of the water in the trough. So this is the volume in the water in the trough. It's a triangular prism that has a height, that's the depth, has a base, there's a volume associated with it. Find the volume of the water in the trough when it is full. So the volume of the water, it's a triangular prism, base times height. And the area of the base is triangle 1/2 base times height times the height, which is really like the length of the prism because it's sideways. And since that's always 5 no matter what, let's plug that in right now. One less variable because it's different h than this. We'd have 3 variables that the derivative would be horrible. And then we kind of want it to be one variable. This is kind of like the cone problems that we have similar triangles here, right? So there's the big triangle for the trough, and then the smaller triangle for the amount of water in there. And so we can say base over height equals 2 over 3. And then we could get it in terms of one variable. Now we can look later on and see what we're going to do. H. So probably want H. So base equals 2/3 H. Plug that in to our volume formula. Earlier is better than later. So base 2/3 H, and then we have 5. So that's going to equal, the 2's cancel, 5. Oh shoot. I did the wrong thing. Okay, let's try this again. 1/2. I'm changing the base to 2/3 h. And then we have the h. And then we have the 5. So 2's cancel. So we have 5/3 h squared. That's the volume formula. I think that will be helpful. So when it's full, part A, the height is 3. So when those 3's cancel, we get 15 cubic feet. That's the volume when it's full. All right. B says, what is the rate of change at H at the instance when the trough is a quarter full by volume? So we're going to take the derivative of this. That's not going to be very hard. We can go and do that right now. So it's going to be dv dt equals 10/3 h dh dt. And dv dt, we already wrote down, was -2. But we don't know what h is when it's a quarter full. Don't put 3 in. So we got to figure out what that height is when it's a quarter full. So if this is the volume when it's full, a quarter full would be 1/4 of that. And then you could set that equal to the equation for the volume in terms of h. So you can figure out what the h is when it's a quarter full. So multiply by 3/5 and take the square root of both sides. So the 5 is going to be 9/4. It's going to be the square root plus or minus h equals positive. We want to do the positive height, 3/2. So 3/2. Those cancel. This becomes a 5. Solve for dh dt equals -2/5. Units of height should be one-dimensional. Feet per time is minutes. There you go. C says, what is the rate of change of the area of the surface of the water shaded in the figure at the instance when the trough is quarter full by volume? So the area, the rate of change of the area. So the area we're talking about is this top area, which is a rectangle, right? And it's whatever the base is times the length, which is always 5. So it's 5b. But it might be good to get it in terms of h, since we know everything about h, so that might be a little more convenient. But earlier we said b equals 2/3 h. So I'm going to plug in 2/3 h. So it's going to be 10/3 h. So this is the area that we're talking about in terms of variables that we've already found a lot of information for. So we're going to take the derivative with respect to time implicitly. It's going to be 10/3 dh dt. This is what we're looking for, dA dt. So dHc we just found, -2/5. And we don't actually need the height. So dA dt is going to be -4/3. The units are area, feet squared, over time. It's minutes. And it's negative because it should be getting smaller because the area, the water's coming out. It's the water level's going down. The area that square on top gets smaller and smaller. So there you go. Last one, tightrope walker. So this problem was actually on the AP test back in 1991. Mr. Statham, who was teaching the class at that point, because I was in middle school, he said, like, no one got it. They all overthought it, or at least part C specifically. So, tightrope walker 30 feet above the ground between the J&T buildings, which are 50 feet apart. Tightrope walker walking at a constant rate of 2 feet per second from point A to point B is illuminated by spotlight 70 feet above point A as shown in the diagram. So I had a bunch of stuff and said, okay, this is light, 50 feet apart, a bunch of the other measurements already on there. This is a tightrope walker. They're walking from A to B. And then they have a shadow down here, right? And they're walking at 2 feet per second. And so on part A, it says, how fast is the shadow of the tightrope walker's feet moving along ground when she's midway between buildings? Indicate units of measurement. So how fast the tightrope walker? So we had to create some variables to associate with the rate they gave us and the rate we're trying to find. So we have this rate, so we put a variable here. You could put it here too, in either one of these. Here, dxdt is positive 2 feet per second. Here, if you put it here, it'd be negative. I think it's better to put it here because you can see the triangles and stuff that you're probably going to use to connect these variables together. So you probably want to work with these triangles right here. And I need this rate right here, which would be tied to this variable. So I called that y, and so we're looking for dy dt. So the first thing we need to do is relate these x and y together before we bring calculus into it. So it's similar triangles, right? And so the ratios of corresponding sides of similar triangles are constant. They're proportional, meaning they all have the same. So we can set this up a lot of different ways. We could say x over 70, this over this equals this over the whole thing, y over 100, right? So you just want to make sure you match up the same sides in the same ways. You can do a lot. You can say x over y equals 70 over 100. You can involve the hypotenuse, which I wouldn't do because that sounds like a lot of extra work. So now I'm just going to make this a little nicer and cross multiply because they're just numbers. And we're trying to find dy dt, so we could even go as far as we could solve for y. So we could say, okay, well, y equals 10/7 x. And then we're going to take the derivative of that implicitly with respect to time. Dy dt equals 10/7 dx dt. And we know dx dt is positive 2. That was the rate they gave us that we labeled. And so dy dt equals 20/7. The units are feet per second. That's how fast her shadow, the foot of her shadow, is moving. So that's part A. I mean, that was kind of weird in itself. B says, how far from point A? Now, by the way, it said when she's midway between buildings, which means that the x would actually equal midway between buildings, means that x has to be 25, right? We didn't even use that because the x went away. We had a dx dt. How far from point A is the tightrope walker when the shadow of her feet reaches the base of the T building? Okay, how far away? So she's going to keep going, and then at some point it says the shadow of her feet reaches the base. So as she's moving along here, eventually her shadow's right here, and her shadow's like right on the building, and her feet's right there. So we're trying to figure out when is that. So I draw it there. This isn't calculus, this is geometry. But we're going to probably use those same similar triangles because we're trying to figure out what is x when y equals 50, right? Because y would be all the way here. And then we're trying to figure out what the x value is. So we're going to use the same similar triangles. The, x over 70 equals y over 100. And we're going to plug 50 in. So we're just trying to find a missing side of similar triangles. So that's going to be 1/2. So x is going to be 35 feet. Now, I'm not boxing the x because that's a variable I created. Someone else might have used x for something else. So maybe we need this for something else. I don't know. We'll see. Part C is the crazy part. How fast is the shadow of the tightrope walker's feet moving up the wall of the T building when she's 10 feet from point B? So if she keeps going, now her shadow is going up the building. As she gets closer to it. In fact, right when she gets here, the shadow's gonna be right in front of her, right? So I'm gonna draw another picture of this because it's starting to get a little crazy. Let's see. I'm just gonna draw another picture because we have a lot of other stuff from the other parts on there, just to kind of focus on this issue. So here's the issue. Her shadow, she's here. Her shadow's here, and her shadow is now moving up the building. She's still moving 2 feet per second that way. That's still the same. This is still 70. This is 30. The whole thing is 50. It says that she is 10 feet from point B. So this is going to be 10 feet, which means this is 40 feet. But just at the end, those things are changing, so be careful. You still get right triangles, and you still get similar right triangles, but they're not, it's a little different. The little one was inside the big one. Now the little one's over here, upside down, inverted from the big one. But these are similar triangles. They share two angles that are the same, another pair of angles the same, another pair of angles, angle, postulate. They're similar triangles. So we're trying to find this now. Now I'm going to create a new variable for this. You could put it here, or you could put it here. I think it would be easier to put it here. And so then this is going to be dz dt. It's going to come out negative. And I'm probably going to take the negative off of it. But the only way it comes out negative is because this length is getting smaller. If I put it down here, it come out positive. I just think it's more convenient to put it here. If I put it here, then I have to have a 30 minus z here, which I think is a little harder to deal with. Now my solutions, I think I put it down here. So if you want to see the difference. Now I'm still using this x over here. The y thing is gone because that triangle doesn't really exist anymore in this situation. So we need to set up our similar triangles. So I'm going to say x over, now don't put 10 here. 10 and 40 need to come in later. Those are not constants. Okay, so before you've done your derivative, you can't put anything that's changing. So if this is x, this is 50 minus x, right? So I could say x over 50 minus x. I could say this over this equals this over this. So you just got to match them up the same way, however you decide to do it. So, I mean, that's one way. I mean, you could do x over 70 equals 50 minus x over z. It's another way, but it's going to give you the same thing in the end. So I'm just going to go with this. I'm going to go ahead and cross multiply xz equals 3500 minus 70x. We're looking for dz dt. We have dx dt, so I think at some point we could go ahead and, start taking the derivative. I mean, we could even go as far as to get z by itself. Now, if you did that, I would probably rewrite this as like that, because you could do quotient rule if you want, but negative exponents are a lot easier than quotient rule. So I'm gonna do it like that. Let's see. Didn't make a mistake or anything, did I? 500. Okay. So my work on my solutions I'm uploading is a little different because I put the z in a different place, but we should get the same thing when we're done. dz dt equals negative 3500 x to the negative 2 dx dt. The derivative of negative 70 is 0, so that drops out. So dz dt equals negative 3500. I'm going to put the x squared in the bottom. X is 40, right? X is 40 because she's 10 feet away from B, so x is 40. That's when the 40 comes in. dx dt is the same positive 2 feet per second that we had right from the beginning. Okay, so this is going to be what, 1600. We could divide a 10 out of the top and bottom, another 10 out of the top and bottom. 2 out of this is going to be 8. So dz dt equals, now it says negative 35 over 8 feet per second. But I wouldn't write it like that with the negative, because it's negative because of where we put the z. So I would say, I'd put it in words. The shadow, and by the way, fast is speed. So speed is always positive. The shadow is moving up the wall at a rate of positive 35/8 feet per second. Just to make sure, like I said, the letters we pick, where we put them, can change our answers. And so I think it's better to not have the negative. There you go. That was a challenge problem. Not one student got that one right back in 1991 from Rio Grande High School. Part C, specifically. But this whole problem is definitely challenging. So I hope that all helped.